Now, our next example, 9.22, on page 368, will be a little more complicated, but nothing crazy, guys. Nothing crazy. I mean, it's just one component, one more element we'll have to find to figure out the empirical formula of the substance. So this is what the question is now. The compound acetone, I know from my experience, acetone contains carbon, hydrogen, and oxygen. And so it says, well, actually it's stated here, carbon, hydrogen, oxygen. Compound that is an excellent solvent for a variety of substances. Combustion analysis of 10.0 grams of sample of acetone. So here's what's given. So we're given 10.00 grams of acetone. And so this acetone yields, again, same apparatus used as in the previous problem. It yields 22.75 grams of CO2. It also produces 9.314 grams of H2O. Okay, great. So again, as in the previous problem, what we can do is convert everything to moles and pretty much get the moles of carbon, hydrogen. Here's the problem though. The problem here now is that we got one more element, and we cannot just use the amount of CO2 or H2O to figure out this oxygen, because some of the oxygen that formed the CO2 and H2O came from the outside source, from the oxygen tank. So we can't really use this amount of CO2 and do the same conversions that we've done before. You just simply get the moles of oxygen and said, voila, we just, solve the problem. It's not going to work this way. So in this kind of situation, the first thing you will have to find the grams of carbon, grams of hydrogen, and then since you got the total mass of the whole compound, which in itself includes carbon, hydrogen, oxygen, you will just take that mass minus mass of the sum of the masses of carbon and hydrogen. You will now get the mass of the oxygen. So once you got the masses of each element, you can successfully turn into the moles of this, grams into the moles, and then you will do the same routine as we've done before to figure out the empirical formula of the substance. Again, nothing crazy here. I've taught you already. I gave you some basic skills on how to do these conversions, so you should be able to do this, guys. All right, so let's start with the CO2. We're going to figure it out now, the grams of carbon from here. And again, the first step will be, as always, 1 mole of CO2 contains 44.01 grams of CO2. Canceled. Next, 1 mole of CO2 will contain 1 mole of carbon. And then we need the grams, of course, because we need to get the grams of that oxygen that came straight from the burning of this acetone substance. So 1 mole of carbon is 12.01 grams of carbon. Canceled. So we'll get in a moment the answer here. We're going to do the same procedure here for the water molecule. 18.02. Got a little mistake here. Grams of H2O. Canceled. Again, don't forget grams. Times now 1 mole of H2O contains, don't forget, 2 moles of hydrogen here. And then times 1 mole of hydrogen is 1.008 grams of hydrogen. Canceled. And so let's find out the masses of each element in this particular compound. So that will be 22.75 divided by 44.01, and then times 12.01. I got 4 significant figures here, so that will be 6.208, and I'm going to put a little 3 here, which is not significant, but I want to have it here, grams of carbon. So the next thing is 9.314 divided by 18.02 times 2, and then times 1.008. All right, so I got also 4 significant figures, 1.04, and I got a little, again, 4 significant figures, 2, a little 0 here, grams of hydrogen. Okay, great. Now, so I got the grams of carbon, grams of hydrogen. The only thing is missing is a gram of oxygen. All right, let's find the grams mass. I'm going to put in grams of oxygen. again, since the 10 grams represented the total mass of this compound that contains of carbon, hydrogen, and oxygen, I'm going to say 10.00 grams total minus the sum of 6.2 08 little 3 grams of carbon plus 1.042 little 0 grams of hydrogen. So in terms of significant figures after this step, because this number, we're going to go by precision here because it's a plus or minus operation, so we are going to use precision rules in here. So my final answer here will be rounded off to the hundredths place. All right, so let's do this. 10 minus 6.2083, and then minus 1.042. And so here I got now 2.7. So again, I want to round it off to the hundredth place because of the rule of significant figures. That will be, looks like 7.5, and I want to leave a little digit extra because it's an intermediate result. We talked about it before. Little 0 here, and it will be grams of oxygen. Okay, so I'm almost there, guys. So now I got my grams of each element, so I'm going to turn them into the moles, divide by the small number of moles, and then I should be able to get my empirical formula. All right, let's do it. So my next step, let me just separate these, these steps from each other. So I'm going to say now moles, I'm going to put N, it stands for moles of carbon, and it's equal to now 6.208 little 3 grams of carbon times, as we've done, usual procedure, guys. 1 mole of carbon, 12.01 grams of carbon, cancelled. We're going to get the moles in here in a moment. Now we're going to do the same thing for the moles of hydrogen. We're going to say that 1.042 little 0 grams of hydrogen times 1 mole of hydrogen, 1.008 grams of hydrogen, cancelled. We're going to get that in a moment. And number of moles of oxygen now, since we got the proper grams now, 7.5 little 0 grams of oxygen. We're going to do 1 mole of oxygen is 16.00 grams of oxygen. And so we're almost there. Just be a little patient. So 6.2083 divided by 12.01. So our first answer here, 4 significant figures, 0.5169 a little 3. That will be our moles. Moles, I already know it's moles of carbon in here. Okay, great. So next one. Let's move to the next one. Okay, so that will be now 1.042 divided by 1.008. Okay, so that 1.033 and a little 7 here, moles. Again, moles of hydrogen. And the next one will be 2.75 divided by 16. And then we got 0.171 a little. So we got how many? 3 significant figures here, of course. 7.179 moles, and that will be the moles of oxygen. All right, we're almost there. So remember, guys, we have C, H, and O. Okay, so now I got the moles, and the next step, as usual in empirical formula calculations, is to find the small number of moles of the element present in the compound. And you use that number, divide every other moles of the other elements, and then you will get your empirical formula. All right, let's do it. So this one is 0.5169 little 3. Hydrogen is 1.033 little 7. Oxygen is 0.171 little 9. All right, so which one is the smallest? Looks like this one here, oxygen. I'm going to divide all of them by that number, 9.1719. 0.1719. All right, let's do it now. So 0.51693 divided by 0.1719. All right, let's see. That gives me C3. That looks very good. Now 1.0337 divided by 0.171, again 9. That gave me 6. And then the last one, it's actually divide 0.71 by the same 9 by the same number, so it gives you just 1. And that would be your guys' empirical formula from now more complicated I guess process in which the substance not only had carbon and hydrogen but also oxygen in its molecular formula or empirical formula, in this case empirical formula, and so that's how you determine in such cases.